Hello, my name is Samuel Lee, and today I'll be going over every part of question 1 of exam 2. So, if you recall, it's a problem that's talking about two masses, mass 1 and mass 2, that are attached to two pulleys in a system and set up as shown. And when mass 1 is dropped, pulley 2 and mass 2 moves to the right. And we're being asked to find the acceleration of mass 1. Now, if you recall, force equals mass times acceleration. So, if we're going to have to figure this out, we're going to have to think about forces. And thinking about forces usually leads us to draw a free body diagram. So let's draw free body diagrams. Let's draw one from mass 2 first. For mass 2, we have the tension force acts in this way. Tension 2, namely normal force from the ground and gravitational force of mass 2. Let's call this direction the positive x direction because it'll be just easier to call the direction the system is moving in positive. So the sum of the y forces ends up being 0 because it moves along the table. Which means that normal force minus gravitational force equals 0, or that the normal force is equal to mass 2 times g. And this will be important later on in this problem. Now for the x direction, we can use the same approach and find out that tension 2, the only force in the x direction, is equal to mass 2 times its acceleration of 2. Now let's draw one for a pulley because we don't have enough information yet. T1 acts in this way, T2 acts in this way because there are two ropes. So we can use Fx equals max, but since there is no mass for the pulley, this just ends up being 0. So we end up having T1 minus 2T2 is equal to 0. We can even just say that they're equal to each other. And let's look at the last one, which is mass 1. We need to know more about tension 1, and mass 1 is attached to tension 1. And since it moves down, we can call this positive because we said in the beginning that the direction it moves in is going to be positive. So we end up getting mass 1 g minus T1 is equal to M1A, or that tension 1 is equal to mass 1 g minus mass 1A. Now we know each quantity, let's just plug those in. M1 g minus. And we soon come to realize that there is a problem. Problem being that we don't know either of those accelerations. If only there was a way to derive some relationship between them. Unfortunately, we can. Here's why. When you drop the mass a distance, let's say we agree that the pulley should move the distance this way along the top rope, but it should also move the same amount of distance along the bottom rope. So really, the rope is tugging mass 2 along by a distance of 2d. In the same time, it takes mass 1 to drop that distance. We end up getting these relationships as a result. And since the problem gives us the values for each mass, we can plug all of those in. Finally, we're getting somewhere. And from here, it's smooth sailing because all we can do is solve for A1. And we get that A1 is equal to G over 17, and that's our final answer, part A. Now we know the relationship between both accelerations, and we know what A1 is. We can plug these in and find what T2 is. T2 ends up being 4m times 2 times acceleration of mass 1, and we end up getting for part B, 8g over 17. Cool. Now, part C asks us to find the final velocity of mass 2 once mass 1 has been dropped. One way to do this is my favorite way, the law of conservation of energy, because it shows a direct relationship of the velocities, but I mean, you don't have to solve this way, but I like solving this way. Anyways, we set up our equation. Let's think about this. So it starts at rest. meaning that there shouldn't be any kinetic energy to begin with. The problem also states no external work forces. And if we call the distance it drops the initial height and the final height 0, we end up getting no final potential energy, but potential energy at the beginning for mass 1. The blocks are going to be moving by the time they drop a distance, so we end up getting 1/2 mass 1 v1 squared plus mass 2 v2 squared as the total kinetic energy of the system at the end. Since we know the relationships, we can plug everything in. And get that mgd is equal to 17 over 8 mass velocity squared. I'm speeding this up because I have to get to the other parts. And if we carry out the calculations for velocity 2, we end up getting that 8gd over 17 is our final answer. Okay, so now part D asks us to imagine that there's friction on the surface that mass 2 is moving along. It asks us to find the value of the coefficient of static friction. It has to be below so that the system can move. To find this, we have to find out the this coefficient in which the system is barely moving, and when it's barely moving, that means the total acceleration is 0. For mass 2, a new force is added, friction, as I've written up there. We have that T2 minus force of static friction is equal to 0, or T2 is equal to Fs. Since the sum of these forces ends up being 0 anyway, we still have the same relationship from before. And this time, T1 is equal to M1G because they're equal, because they must cancel each out to bring us a total force of 0. So now we can plug these in. Force of static friction is just mu s normal force, which, as we found earlier in the problem, is m2g. So we end up getting mg is equal to 2 times 4m g mu s, or mu s is equal to 1/8, and that was our answer to D. Now let's move on to part E. Part E asks us to find the velocity of block 2, but with friction, kinetic friction, and let's assume that static friction, this coefficient is lower than what we just found. Well, notice that it's just the same problem, but this time we have friction added. So this time we have to work with external forces, but otherwise the energies before and after the system moves will be the same. Like that, there shouldn't be G there. What is work external forces? Well, it's just force of kinetic friction times the distance it travels times the cosine of the angle between that force and the velocity of mass 2. And since the friction is moving left while mass 2 will end up moving right, this angle ends up being 180, which means that it's just negative FKD. FK is just coefficient of kinetic friction times the distance it travels, and the distance it travels when mass 1 drops the distance t is 2d. So we end up getting minus 2 uk m2g. m2 is just 4m, so this ends up being negative 8m mu k g. Carry what we just found from the top, and now we can solve for v2. Speeding up the calculations gives us that the velocity of 2 is equal to 8g d1 minus 8 mu k over 17, and the square root of that is our final answer.